Hello everyone, I am Nikita Nayak from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In previous video lecture, we learnt about combination and some examples. Today we are going to learn about some important theorems. Before going to theorem, we have one remark. If A and B are mutually exclusive events, that is disjoint events, then A intersection B equal to 5. Mutually exclusive event, that is the occurrence of one event prohibits the occurrence of second event. So A intersection B equal to 5 because there is no common element. So probability of A intersection B equal to P of 5 equal to 0. Now theorem number 1, addition theorem of probability or theorem of total probability. The statement is, if A and B are two events which are not disjoint defined on a finite sample space U. Sample space, that is the set of all possible outcomes. Then probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. So here we have given two events A and B, and we have to prove that probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. A union B, that is A or B. A intersection B, that is A and B. Now we know that A union B equal to A union A complement intersection B, because suppose we have some sample space U and two event A and B. Now this part is A intersection B and complement of A, that is the part of U which is not including A. So this is our A complement. So intersection of A bar and B, that is only B. So we can write B equal to A bar intersection B. Now the probability of A union B equal to P of A plus P of A bar intersection B. And for getting P of A intersection B, we add and subtract by P of A intersection B. So we get P of A plus P of A bar intersection B plus P of A intersection B minus P of A intersection B. And as we know that P of A intersection B plus P of A intersection B equal to P of B, we get P of A union B equal to P of A plus P of B minus P of A intersection B. Now we have corollary 1. If A and B are mutually exclusive events, that is disjoint events, then A intersection B equal to 5, because mutually exclusive event means the occurrence of first event is prohibits to occurrence of second event, or occurrence of second event prohibits occurrence of first event. So probability of A intersection B equal to P of 5 equal to 0. So statement of theorem becomes P of A union B equal to P of A plus P of B. P of A intersection B equal to 0. So P of A union B equal to P of A plus P of B. Now second corollary, if A and B are mutually exclusive event and exhaustive events, then A union B equal to U and A intersection B equal to 5. In events, that means at least one event occurs. So P of A union B equal to P of U equal to 1 and P of A intersection B equal to P of 5 and which equal to 0. So in this theorem P of A union B equal to 1. So P of A union B equal to 1 and P of A plus P of B as it is and P of A intersection B equal to 0. So our statement becomes 1 equal to P of A plus B of B. Okay, now the one question arises in mind is whenever we use the addition theorem. So whenever we have to find probability of A union B, probability of A or B, probability of either A or B, probability of at least one and probability of A plus B, we use the addition theorem of probability. Now theorem 2. If A is any event defined on finite sample space U, sample space is the set of all possible outcomes, then probability of A complement is equal to 1 minus probability of A or probability of A equal to 1 minus probability of A dash, where A dash is the complementary event of A. Complement event is the event which is containing of all points of sample space S which are not in A. So now proof. Here A is any event defined on finite sample space U and A dash is the complementary event of A. As we know, A union A dash equal to U because complement of A is an event which is consisting of all points in S or sample space U but not in A. So A union A dash equal to U. Therefore, probability of A union A dash equal to probability of U. And as we know, probability of U equal to 1, probability of A union A dash equal to 1. Now give equation number star. Now we know that probability of A union A dash equal to probability of A plus probability of A dash minus probability of A intersection A dash from additive theorem. Give equation number double star. As A dash is the complement event of A, the intersection of A and A dash is 5. That is A and A dash are mutually exclusive event. So probability of A intersection A dash equal to P of 5 equal to 0. Give equation number triple star. Now from this equation double star become probability of A union A dash equal to probability of A plus probability of A dash minus this term is 0. So we have probability of A union A dash equal to probability of A plus probability of A dash. Give equation fourth star. Now from equation star, that is probability of A union A dash equal to 1 and equation number 4 star, which is probability of A union A dash equal to P of A plus P of A dash. We have P of A plus P of A dash equal to 1. Therefore, P of A dash equal to 1 minus P of A or P of A equal to 1 minus P of A dash. Now, theorem number 3. Prove that 0 less or equal to probability of A is less or equal to 1. Let a random experiment have n outcomes. From these n outcomes are favorable to event A. Favorable event, that is the event which are winning event. Now definition of probability. We know that probability of A equal to favorable outcomes over total outcomes. So probability of A equal to favorable outcomes m and total outcome n. So probability of A m by n. Now m outcomes are from n outcomes. So m varies from 0 to n because total outcomes are n. So 0 less or equal to m less or equal to n. But here we need probability of a, and probability of a equal to m by n. So we multiply this whole term by 1 by n. So we get 0 over n is less or equal to m over n is less or equal to n over n. But 0 over n is 0, m by n as it is, and n by n that is 1. So we have 0 less or equal to m by n is less or equal to 1, and m by n is nothing but the probability of a. So we get 0 less or equal to probability of a less or equal to 1. That means probability of any event is between 0 to 1. Now we have some remarks. If A, B and C are three events defined on finite sample space U, sample space that is set of all possible outcomes, then number 1, probability of A union B union C equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. Now number 2, if A, B and C are mutually exclusive event. Okay, mutually exclusive event, that is the intersection of their both event or all events is 5. So here we get probability of A union B union C equal to probability of A plus probability of B plus probability of C, because as A, B and C are mutually exclusive event, A intersection B equal to 5, A intersection C equal to 5, B intersection C equal to 5, and A intersection B intersection C equal to 5. And as we know, probability of 5 equal to 0. So we get probability of A union B union C equal to probability of A plus probability of B plus probability of C. Now number 3, if A, B and C are mutually exclusive and exhaustive event, then if we have mutually exclusive and exhaustive event, then we have intersection of these events is 5 and union of this event is U, that is our sample space. So here we get probability of A union B union C equal to probability of A plus probability of B plus probability of C, because probability of A intersection B, probability of B intersection C, probability of C intersection A is 0, and probability of A intersection B intersection C is also 0. And as we know, if we have exhaustive event, then that equal to probability of U, and probability of U equal to 1. Now next one, in general, if A1, A2 up to An are mutually exclusive events, then probability of A1 union A2 union up to union An equal to probability of A1 plus probability of A2 plus up to plus probability of An. Here also we can write probability of A1 union A2 union up to union An equal to probability of A1 plus A2 plus up to plus An. Similarly, here we can also write probability of A union B union C equal to probability of A plus B plus C. Now, if A subset B, then probability of B minus A equal to probability of B minus probability of A, and probability of A is less or equal to probability of B. If A, B are any event in U, U that is our sample that is the set of all possible outcomes. Then number 1, probability of A intersection B dash. B dash that the complement of B equal to probability of A minus probability of A intersection B. Number 2, probability of A dash intersection B. A dash that is the complement of A equal to probability of B minus probability of A intersection B. Number 3, probability of A dash intersection B dash. A dash is the complement event of A and B dash is the complement event of B equal to probability of A union B whole dash. A union B whole dash that is complement of A union B equal to 1 minus probability of A union B. And the last one is probability of A dash union B dash equal to probability of A intersection B whole dash equal to 1 minus probability of A intersection B. These both are nothing but the De Morgan's rule. Let us consider examples. Number 1. If A and B are mutually exclusive events and P of A is equal to 0.30, P of B equal to 0.45, then find the probability of the following events. A dash, B, A intersection B dash, C, A union B, D, A dash intersection B dash, and E, A dash union B dash. Now here, A and B are mutually exclusive events. That is, intersection of both events is phi. So, A intersection B equal to phi. Therefore, probability of A intersection B equal to P of phi equal to 0. Give equation number 1. Also given P of A equal to 0.30. Give equation number 2. And P of B equal to 0.45. Give equation number 3. Now the first one, we have to find probability of A dash. We know that probability of A dash equal to 1 minus probability of A. Give equation number 4. P of A dash equal to 1 as it is, and P of A, that is our equation 2, is 0.30. So we have probability of A dash equal to 1 minus 0.30 equal to 0.70. So probability of A dash equal to 0.70. Now next one is A intersection B dash. We know that probability of A intersection B dash equal to probability of A minus probability of A intersection B. Therefore, probability of A intersection B dash equal to, here we have probability of A equal to 0.30 and probability of A intersection B equal to 0 because A and B are mutually exclusive events. So, probability of A intersection B dash equal to 0.30 minus 0. Therefore, probability of A intersection B dash equal to 0.30. Now next one is A union B. We know that probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. This is the statement of addition theorem for probability. Therefore, probability of A union B equal to, here we have probability of A equal to 0.30 plus probability of B equal to 0.45 and probability of A intersection B equal to 0 since A and B are mutually exclusive events. So, probability of A union B equal to 0.30 plus 0.45 minus 0 equal to 0.75. Therefore, probability of A union B equal to 0.75. Give equation number Fine. Now next one is A dash intersection B dash. We know that probability of A dash intersection B dash equal to probability of A union B whole dash. This is the De Morgan's rule. And by our equation 4, we know that probability of A dash equal to 1 minus probability of A. But in place of A, here we have A union B. So probability of A dash intersection B dash equal to 1 minus probability of A union B. Already we have probability of A union B equal to 0.75. So probability of A dash intersection B dash equal to 1 minus 0.75 equal to 0.25. So probability of A dash intersection B dash equal to 0.25. Now the next one is A dash union B dash. We know that probability of A dash union B dash equal to probability of A intersection B whole dash. This is the De Morgan's rule. But by theorem, we know that probability of A dash equal to 1 minus probability of A. Here in place of A, we have A intersection B. So probability of A dash union B dash equal to 1 minus probability of A intersection B. And probability of A intersection B equal to 0 because A and B are mutually exclusive events. So probability of A dash union B dash equal to 1 minus 0 equal to 1. So probability of A dash union B dash equal to 1. Example 2. Two people are selected at random from a group of 7 men and 5 women. Find the probability that both are men or both are women. Let A represent the event that both are men and B represent the event that both are women. Now A intersection B, that is A and B, represents the event that both are men and women. But the events A and B are mutually exclusive events because it is impossible that both people are men and women too. So A intersection B equal to 5. Therefore, probability of A intersection B equal to probability of 5 equal to 0. Give equation number 1. Now A union B, that is A or B, represents the event that both are men or both are women. Here we have to find the probability that both are men or both are women. So we have to find probability of A union B, and by addition theorem of probability, we know that probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Okay. Here we have total 7 men, and out of 7 men we have to select only 2 men. So favorable outcomes are 7C2. See that is combination, and here order is not important. So we calculate the combination. Combination is denoted by NCK or NCK. Right? So here favorable outcomes are 7C2 and here we have total 12 persons because 7 women men and 5 women. So total outcomes are 12C2. Therefore probability of A equal to 7C2 over 12C2. Now probability of B, that is both are women. Total women are 5. So favorable outcomes are 5C2 because out of 5 women we have select only 2, and as we know total outcomes are 12C2, and probability of A intersection B we already find 0. So probability of A union B equal to 7C2 over 12C2 plus 5C2 over 12C2. Therefore, we have to find 7C2, 12C2 and 5C2 using calculator directly. Otherwise, 7C2, that is 7 factorial over 7 minus 2, 5 factorial into 2 factorial. 7 factorial, that is 7 into 6 into 5 factorial over 5 factorial into 2 factorial as it is. So 5 factorial cancel out. 2 factorial, that is 2 into 1. So 2 cancel out, we have 3. Therefore 7 into 3 equal to 21. So 7C2 equal to 21. Now 12C2, that is 12 factorial over 12 minus 2, that is 10 factorial into 2 factorial, and 12 factorial we can write 12 into 11 into 10 factorial over 10 factorial into 2 factorial as it is. So 10 factorial cancel out. 2 factorial is 2 into 1. So 2 cancel out, that is 6, and 11 into 6 equal to 66, and 66 by 1, that is 66. So 12C2 equal to 66. Now the next one is 5C2. 5C2, that is 5 factorial over 5 minus 2 equal to 3 factorial into 2 factorial. 5 factorial we can write 5 into 4 into 3 factorial over 3 factorial into 2 factorial. Now 3 factorial cancel out, and 2 factorial, that is 2 into 1. So 2 cancel out, we have 5 into 2 equal to 10. So 5C2 equal to 10, and 12C2 already we find 66. So probability of B equal to 10 over 66. Now here denominator is same. So we have to take LCM. So we have 21 plus 10 in numerator and denominator is 66. So probability of A union B equal to 31 over 66. So probability that both are men or both are women is 31 over 66. Now the next example is, are the following events mutually exclusive? Here we have given first one, event E, a person having a birthday in February, and event F, a person having a birthday on 13th of a month. As we know, a February month is consisting of only 28 days, and in a leap year we have 29 days in February month. But the event F is birthday on 13th. So it is impossible that a February has date 30. So E and F are mutually exclusive events. Now the second one is, event E is selecting a student who is taking English, and event F is selecting a student who are not mutually exclusive events because a student who is taking English is also take maths. Now example 4. A survey of couples in a Kerala state found the following. The probability that the husband has a college degree is 0.65 and the probability that the wife has a college degree is 0.70. The probability that both have a college degree is 0.50. A couple is selected at random. A. Find the probability that at least one has a college degree. And B. Find the probability that neither has a college degree. Here, let capital H represent the event that the husband has a college degree and W represent the event that the wife has a college degree and H intersection W represents the event that husband and wife both have a college degree. Here we have given the probability of the husband has a college degree is 0.65. So, probability of H equal to 0.65. Also we have given the wife has a college degree is 0.70. So probability of W equal to 0.70 and probability that both have a college degree is 0.50. So probability of H intersection W equal to 0.50. Now we have to find the probability that at least one has a college degree. At least one, that is, if a husband has a college degree, if the wife has a college degree, or both have college degree. That is either H, either W, either H intersection W. So, the H union W. That is, here we have to find probability of H union W. So, H union W represent the event that at least one has a college degree. And by addition theorem of probability, we know that probability of H union W equal to probability of H plus probability of W minus probability of H intersection W. Already we have probability of H equal to 0.65, probability of W equal to 0.70 and probability of H intersection W equal to 0.50. So, probability of H union W equal to 0.65 plus 0.70 minus 0.50 is equal to 0.85. So, probability of H union W equal to 0.85. That is, the probability that at least one has a college degree is 0.85. Now, find the probability that neither has a college degree. Right? Know that at least one has a college degree, that is, wife has a college degree or husband has a college degree or both have college degree. So, probability of neither has a college degree equal to 1 minus probability of at least one has a college degree is equal to 1 minus probability of H union W. And already we find probability of H union W equal to 0.85. So, probability of neither has a college degree equal to 1 minus 0.85 equal to 0.15. Therefore, the probability of neither has a college degree is 0.50. In next video lecture, we will will learn